Basically, migration improves horizontal resolution by focusing energy spread over a Fresnel zone, repositioning out-of-place reflections caused by dip, and collapsing diffractions from points and edges. Collapsing energy from diffractions and focusing energy spread over Fresnel zones make amplitudes more accurate and more directly indicative of reservoir properties. We usually take a few binned stack lines from a crucial part of the prospect and migrate the lines in 2 dimensions, using migration velocities that are 90 to 95% of the stacking velocities. Then we inspect the results for evidence of under and over migration. Under-migrated seismic data will show an incomplete collapse of point and fault diffractions, suggesting that the velocity field is too slow. Conversely, over-migrated data caused by applying a velocity field that is too fast will show small inverted diffraction cones, or smiles.
When the 2D test lines finally appear to be migrated properly, we can run the data through a full 3D migration scheme. But since the results of migration are so important in 3D surveys, let's state a few rules of thumb for migration. First, there are 2 basic types of seismic migration: time migration and depth migration.
Time migration is less expensive than depth migration, but if there are lateral velocity variations, you must use depth migration. Second, migration before stack versus after stack greatly improves data quality in structurally complex areas. There are 3 principal time migration methods: Kirchhoff, finite difference or downward continuation, and Fourier transform or frequency domain. The advantages of using a Kirchhoff migration scheme include its simplicity and its ability to handle steep dips. The finite difference method can handle data that have low signal-to-noise ratios and small lateral velocity variations. The advantages of using a Fourier transform method include its relatively short computing time, its ability to produce good results when the signal-to-noise ratio is low, and its ability to handle steep dips.
But all of these time migration methods have a common disadvantage. None of them can handle even moderate lateral velocity variations. So how do we reliably migrate data if these variations exist? We use a process called depth migration.
There are a number of depth migration schemes, such as finite difference, ray theoretical, image ray tracing, and phase shift plus interpolation migration. In depth migration schemes, if the velocity model is accurate, and we hope it will be with a 3D survey, then the depth-migrated results are an improvement over time-migrated data. However, running a depth migration program is time-consuming and expensive. For instance, a 2D line may require 50% more computing time and money for a depth migration than for a time migration. On 3D data, the disparity can be even greater. So how do we decide which depth or time migration method to use? We could make a case for using a fast and economical migration as a first pass. Then on subsets of the data volume, where the geologic objective and complexity of the acoustic wave field warrants special attention, we can use a more expensive and accurate migration technique. And we need to mention one more method used to migrate data: 2-pass migration. Because 3D data are binned, we can apply the migration process in 2 passes. First, we migrate the inlines just as if the data were 2D in origin. Then we gather traces from the 3D data volume into crosslines and rerun the migration in this direction. Although there are technical arguments against the 2-pass approach, it uses significantly less computer time than the 1-pass approach, which operates on the entire unmigrated data volume simultaneously.